I open the defense of Elham Fadaly, and I request the candidate and assistants to take position behind the desk. Are you ready?
Yeah.
Then we can start. I discovered that I have a screen here in which I can select the camera. So this is a premiere for me. So things might go wrong for the audience, but in any case, I would like to invite the first promoter, Professor Bakkers, to open the opposition.
Geachte promovenda, I would like to ask you if you could present your thesis for a general audience.
Hooggeluide promoter, thank you so much. Okay, so this is the title of my thesis, and in the next 10 minutes, I will try to explain these complicated words that you see here about my thesis. So nowadays, smart devices like our laptops, mobile phones have been at the heart of our daily routine. And especially the past year during the lockdown due to Corona, we have been all heavily dependent on internet data transfer. We're all day doing video calls for work-related matters, connecting remotely with family members, streaming videos from Netflix and YouTube, etc. So this huge amount of data is handled by data centers around the globe, and the electronic devices inside these huge data centers are suffering from a huge amount of energy consumption in the form of heat and also limited communication speed. So the bottleneck in the current technology to transfer data inside these data centers are mainly in the on-chip data communication, where physical wires or electrical interconnects are transferring data inside our electronic devices. So we can say that fast and power-efficient communication mean is needed for that. And if we're talking about fast speeds, nothing is faster than the speed of light. So this can act as a transformative trick to make optical interconnects a viable alternative for the physical electrical interconnects. And in addition to that, light does not produce heat like their electrical counterparts. However, this is not a simple and magical solution as it seems, because if we look to the electronic chips, the brain cells of our electronic devices like PCs and cell phones, they are made of materials called silicon and germanium. And these materials, despite having excellent electronic properties, they have poor optical properties, and they cannot emit light efficiently for data communication. However, if we look to the optical communication, like in the internet, cloud data centers, they heavily depend on other expensive materials, but with excellent optical properties. So one might ask, why not to unite these excellent optical properties and electronic properties in the same material family? And of course, we would like this material family to be in silicon germanium, since they are the cornerstone materials in our electronic devices. In other words, we can say, can't we just unite, can't we just make silicon and germanium emit light efficiently? So, sorry. This puzzling question has been actually in the field for the past 5 decades, and despite the tremendous amounts of efforts, this question has been unanswered till today. And this is mainly because silicon and germanium in their natural structure, as we call it, cubic, as you see in this cartoon here, does not emit light efficiently. However, a very nice hypothesis appeared in the 70s, where scientists theoretically predicted that if we reordered the atoms of silicon and germanium in another structure, interestingly called hexagonal structure, it might emit light efficiently. And if we mix silicon and germanium with certain percentage, this will also lead to with the hexagonal structure to the efficient light emission. So the question is, can we realize these structures experimentally, knowing that they does not exist in nature? This 5 decades years old question has been actually what I've tried to answer during the past 4 years of my PhD. And to realize these structures, I used a technique called so-called crystal transfer technique, where I use a hexagonal template material in the form of a nanopillar, and I call it here a core nanowire, and then I transfer the hexagonal structure to the desired silicon shell growing around it. And to control the atomic ordering in these hexagonal materials, I used a technique called epitaxy. And epitaxy comes from the Greek word meaning epi means above and taxis means in an ordered manner. So if I use a sample, I call it here a substrate, and then I let a flow of gases containing the silicon and germanium atoms on top of my sample, then silicon and germanium atoms attach to my substrate, and I can control that by different growth conditions like temperature, pressure, and gas flows. So here's the timeline of my PhD journey. 4 big milestones starting from the hexagonal core template optimization and until eventually demonstrating efficient light emission from silicon germanium. Starting from the very beginning, you can see that we have managed to grow nice hexagonal template nanowires as a start, and to make sure that they have the right crystal structure, or in other words, the right atomic ordering, we examine it by electron microscope. And as you can see here, these atoms order in a zigzagged manner as in the cartoon on the right. And this is the hallmark of the hexagonal atomic ordering. So we can say as a start, we fabricated defect-free hexagonal core template such that we can now move to the next step, which is the hexagonal shell growth. And as you can see in this nice image, we have nicely ordered hexagonal shaped silicon germanium shells around the cores that we optimized in the first step. And again, to make sure that they have the right atomic ordering, we examine it under the microscope, and we see a very nice continuation of the atoms from the core on the left in blue to the shell in red on the right. And again, they follow the nice zigzagged ordering. So this is not a simple step because we had to dig deeper into the growth dynamics of this material, and this striking result is reported for the first time in the literature to have this high quality hexagonal silicon germanium material. However, interestingly, we found a very interesting observation. If you magnify these structures and look closer, we see partial dark lines running across the diameter of our nanowires. And we found out that this is an unconventional type of partial defect that is seen for the first time in this hexagonal silicon germanium material. So to understand the structural properties of this defect, this is the third step in the whole journey. And we zoomed in these partial dark lines, and we saw that they start randomly at a certain spot in our shell, as indicated by the white arrows here. And when we try to visualize them in 3D, we find out that they form triangular, faulty stacked planes in the pure hexagonal structure. And when we try to look at them from the side views here, we find out that these are lines of atoms ordering in a different order than the hexagonal atoms that we want. So we can say we understood the structural properties of this defect. We figured out the possible formation mechanisms leading to this defect such that we can avoid it in the future. And most importantly, we proved that these defects are harnessed to the optical properties of the material, which takes us to the last step and the most important one in the whole journey, demonstrating efficient light emission from these beautiful materials. And as a start, we fabricated a wide range of hexagonal silicon germanium compositions, as you can see here, starting from pure germanium up to 40% germanium. And the nice hexagonal shape with the flat side walls, it's an indication of high quality crystal material. Then we study the optical properties of these nanopillars by shining light on them, and then we study the emitted light from it by a camera. And the output of this camera is light spectra, as you can see here. And we nicely managed to tune the composition, or let's say the mixture of silicon and germanium in these structures. And we managed to confirm that we can tune the emission range of these different silicon germanium compositions, meaning we can tune the color of the emitted light such that they can act as multiple optical communication channels for data communication. And we also demonstrated for the first time that this emission is efficient light emission from this material. And our experimental results turned out to be in excellent quantitative agreement with the theoretical calculations or predictions that I talked about it at the very beginning. So now we have answered the long-awaited question in the field that has been holy grail for the past 5 decades. What's next? Next is to demonstrate lasing. And this is mainly for 2 main reasons. First, to confirm the excellent properties that we have claimed for our material. And next, to make an on-chip light source for optical data communication. And then this paves the way towards integrated silicon compatibility, silicon compatible technology for scalable electronic devices. And with that, I would like to end my presentation, and I would like to thank you all for your attention.
Thank you very much. Are you satisfied?
Yes, for sure. Thank you.
Thank you.
Thank you very much. The Eindhoven University of Technology is very grateful that also experts from outside our university are willing to take part in defenses like this. In this jury we have Professor Jagadish of the Australian National University, Professor De Boek of the Catholic University of Leuven, and Dr. Vincent of the Université Paris-Saclay. I thank all three of you for being here or being it online, but nevertheless. And I would like to invite Professor Jagadish to continue the opposition.
Thank you, Chair. And Dr. Promavenda, thank you for your presentation. And let me start with a general question. How do you determine a material is a direct band gap material categorically?
Google, the opponent, thank you so much for the question. So we do that by optical characterization method. So we used photoluminescence to determine the directness of the band gap of the material. So we made, my colleagues in the team did the optical characterization, and they did a series of measurements. First, they made the power dependent series to they monitored the optical emission of our nanowires as a function of the power series. And also we did a temperature dependent series to see the characteristics or the evolution of our emission. And by the different results we got, we managed to compare the different results we got from the results that shows like an indirect versus a direct band gap material. Do you want me to dig deeper into details?
Thank you, Dr. Promavenda. And may I ask you the question that how do you ensure that these emissions are not from the point defects, because of the fact that the people have studied silicon and germanium and then identified some point defect emissions in 60s and 70s? I just want to ensure that these are not just the emissions from the defects.
Google, the opponent, thank you for the question. So first of all, we made via collaboration with our colleagues in the University of Vienna that we made electronic band structure calculations to calculate the electronic properties of a pure hexagonal crystal of germanium and another crystal with these I3 defects. And we compared both electronic band structures, and we saw that it does not cause any mid-gap states, and the states are induced in the conduction band. And then when our colleagues did the optical characterization, we found out that with, let's say, different qualities of our nanowires is not really affected by the photoluminescence from the different quality or the different defected samples is not really affected. That's why we concluded that it's not harmless to the optical properties of our material.
Thank you. Dr. Promavenda, and you mentioned that the planar defects have not had an impact on the optical properties. And then I would have thought that these planar defects also can act like scattering centers for the electrons for the carrier transport and other things. Would you like to comment on that one, please?
Yeah. Google, the opponent, thank you for the question. Indeed, that's really the interesting point, that this was the next step in our study, is to study the electronic properties, but we only studied the optical properties at this stage.
Okay, thank you. Dr. Promavenda, and I've observed that the line width of your samples of the silicon with germanium 0.7 and then 0.65 have a broader line width with respect to the other samples, and I would like to know what is the reason for that.
Google, the opponent, thank you for the question. So first of all, I would like to indicate that these specific two samples, they had a parasitic peak coming from the cubic silicon germanium on the substrate. So we had to swipe or mechanically transfer these nanowires on another sapphire substrate to be able to measure it. So let's say all the rest of the compositions were ensembles of as-grown nanowires. However, these two specific samples were single nanowires. So this might be one of the reasons that we see a different behavior than the rest of the samples.
Okay, thank you. Dr. Promavenda, ideally you would like to have semiconductors with no defects. What are the ways we can really get rid of these planar defects which you have studied quite extensively?
Google, the opponent, would you mind if you repeat the question?
sorry, how one can get rid of the planar defects which are present in your samples, but ideally you want to have no defects in the semiconductors if you want to make lasers or any other optoelectronic devices?
Google, the opponent, thank you for the question. So first of all, I would like to indicate that we try to investigate different formation mechanisms for these planar defects. And the most probable two mechanisms affecting these defects, first of all, impurities at the interface of our silicon germanium and gallium arsenide core shell nanowires, and might be the background doping arsenic and gallium from the core or the ambient of the reactor. And the other mechanism is the instabilities in the growth dynamics. So if we make sure to properly control these two mechanisms, reduce the impurities, hopefully by trying, for example, cap the gallium arsenide core properly before we grow the silicon germanium shells, reduce the background doping as much as we can, or get rid of the gallium arsenide core completely, which is the best case scenario. So this is for the first one. And the other thing about the impurities, like for example, because we do a chemical etching that might induce impurities on the interface, we can also grow a gallium arsenide shell to rebear the surface and have a very nice, clean, fresh interface to start with. So this is for the first mechanism. For the second mechanism about the growth instabilities, we saw that we actually investigated two parameters: the temperature. As we grow our shells at higher temperatures, the defects are less. So, and this also reflects on the mobility of the atoms diffusing on the surface of our nanowires, which prefers the layer by layer growth. So higher temperature is desired for getting rid of these defects, or at least reducing their number. The other thing is that we use quite reasonable flows, not very low, because low flows might get us not the proper supersaturation for the growth of the material. So we need relatively high flows and higher temperatures. And not very high, of course, otherwise it will be too much.
Okay, thank you. Let me ask the last question. And then what has limited you, after Promavenda, what has limited you in terms of being able to demonstrate a laser, considering that you've already demonstrated excellent optical properties?
Okay, the opponent. And for that, I would like to show one slide that enumerate the number of reasons that might limit us from showing lasing till now. So the first one is that the end facets of our nanowire. So we have two facets of the nanowire. One of them is, let's say it's atomically flat if we cleave it properly from the substrate because it's along one of the crystallographic direction. The other one, which is the top, it has a cubic silicon germanium top, which is not flat. So this can be one of the reasons that scatter lots of the light. The other one, we need a good heat conduction to the substrate because lots of the emission can be lost to the substrate. And another one, maybe we don't have a sensitive enough detector. Could be that the nanowire emission from our nanowires is not really towards the detector. We also need a good back reflector. The other thing is that we still have a bit of dispersion in the dimensions of our nanowires. They are not perfectly uniform in terms of the length, their order, and also their shell thickness. And yeah, so these are the many reasons that we think why we don't have lasing yet.
Okay, thank you, Dr. Promavenda. Chair, I have asked my questions. Thank you.
Thank you very much, Professor Agadic. Professor De Boek, can I persuade you to continue the opposition?
Thank you very much, Chairman. Geachte Promovenda, my first question goes to one of those beautiful images that you yourself and your colleagues have mastered in this thesis, and it's on EDX. I was quite surprised, and maybe I'll give you the page number. It's page 164, because that's where the image is displayed. And EDX, maybe you can explain briefly to the audience what it means, not in lengthy terms, but we need to talk about the composition that's inside this very beautiful nanowire. And it's the composition of silicon and germanium. And so on the EDX picture, and in that picture you show there, it's number C, for instance, you see what you so poetically call the sunburst effect around the core. But also you see on the image that along the spokes, if you want, of that of the hexagonal wheel, you also see increased germanium content. Now, my question is, first of all, do you worry about it? And secondly, but we come back to that later, what is the impact of that? And as a matter of fact, it's germanium increase in that composition. What is the impact you see in future applications? But first, how does it come about?
The opponent, thank you so much for the questions. I will start with the first question about the EDX. So the EDX we have performed here, we performed it in a transmission electron microscope. So we shoot our sample with high energy electrons, and then we look at the characteristic X-rays emitted from our sample. And then based on the characteristic X-rays from every element, we can map especially the elements in our structure. So we can see here a compositional map from the different elements that exist in our structure. So in the middle, the blue one, you see this is the core material or the hexagonal core template material that we call gallium arsenide. And around it, we have the silicon germanium alloy or mixture. So silicon in green and germanium in red. And we have two different compositions. One of them is germanium is more germanium rich than the other one. So the sample in panel D has more silicon composition than panel C. So this is the first question. So, and the second question about the sunburst regions. These regions are very common in faceted structures, or let's say in core shell nanowires. And we usually attributed it to the different mobilities of the different elements in our alloy. So one of them diffuses faster than the other one in these faceted regions. In our case, germanium probably is more mobile than silicon in this case, such that we have germanium-rich sunburst regions. And coming to the third question about what could be the effect of these sunburst regions or the germanium-rich thin stripes in our structures. So to be honest, we didn't really investigate it in detail, like about the effect of these regions in our optical characterization or electronic characterization. But let's think about it. This germanium has a smaller band gap than silicon germanium. So we might think that carriers might escape to these germanium regions. But to be honest, when we did the optical characterization, we didn't really see a pronounced effect for these regions disturbing the optical characteristics of our structures. Because later on in my thesis, in the same appendix, when we grew the shells around thick cores, we had an inverse enrichment for our samples, such that we had silicon-rich silicon germanium shells. And we saw the exact same optical characteristics for both structures with germanium-rich stripes and with silicon-rich stripes. So I assume that somehow the carriers are blind of these germanium-rich regions.
So thank you for that part of the answer, though I want to go one step beyond, because the germanium-rich regions, you mentioned bandgap, but they will also have different lattice parameters, so they can cause strain. And even though your current characterization tools take sort of an assembly of these nanowires, when you will use them in a laser structure, they each individually are very important in terms of how they behave. So would you think that, just assume that we maybe a decade from now make lasers of these structures, what do you think is the impact on the lasing characteristics of this silicon germanium variation along the spokes and in the center?
The opponent, thank you so much for this question. We actually thought about it, and if we look at the mapping or the line profile across the shells of our across the composition of our shell, we will see there is a variation of 3 to 5% in the alloy composition. And this is almost the same percentage in our sunburst region. So we can say that the enrichment in our sunburst region is already within the alloy fluctuation in the whole structure. So I would say they are very thin until now, and they are not really detrimental to our optical properties. However, in the future, if we think about it, they might be utilized as quantum wells if we engineer it properly. For example, if they are germanium rich. And there are already publications about that.
So now you're making it even more interesting. You say you can engineer it maybe. So what would be the way to engineer these compositions then?
So to be honest, I didn't think about it before, but let's think, for example, if we know that these strand-burst regions appear by the different mixture in our sample, so we can study the different percentages. We can also try to engineer the strain, because we saw, for example, that when the core is very thin, it's germanium rich, and when the core is very thick, it's silicon rich. So there is one parameter here to study and play with. And even to further understand, we might think of, if we know that these sun-burst regions appear in faceted structures, can we have even more facets such that we have more of these sun-burst regions? But I must say that this is one of the drawbacks that we cannot easily get rid of when we have structures or faceted structures, especially when we're working.
Thank you, Dr. Promovenda. It's great to have your expert opinion on this, and it certainly warrants further research and discussion. So on that note, I would like to change to my second question, and it's more on the use case. So let's say, of course, you already described the very important need of having silicon CMOS or silicon technology compatible laser structures, which is what's driving you in this research. And in chapter 8, looking forward, you explained a number of options to make that compatibility even more complete, so to speak. Because we need to admit now your work is starting from a gallium arsenide substrate, and it needs gallium arsenide to be successful. But you gave a number, 4 in total, of ways forward to make that compatibility, as I said, more complete. Now, I'd like to disagree with your choice of the first. Well, you said, the first choice of the 4 would be carry your preference. I would like to, as I said, disagree and maybe push towards your reasoning. Why not the second choice? The second choice being using or starting from a silicon substrate, because that's, of course, where all of the other technology steps will be performed. So can you entertain a bit on how, or elaborate better on how we should understand your choice and why not the others?
Google as the opponent. Thank you so much for the question. I must say that we started with the first choice about having gallium arsenide template, because this has been a very difficult question in the field to answer. That we can indeed have efficient light emission out of hexagonal silicon germanium based on. We started with the viable solution because we know already that in the field that it's ideally choice.
I don't know whether it's for all of us, but the audio is interrupted sometimes.
Do you hear me clearer now?
I hear you now, but it's sometimes interrupted. So maybe please speak slowly. I hope it comes through. Thank you.
Oh, I'm sorry for that. Okay, I will repeat my answer. So I'll start again. So our choice with starting with a gallium arsenide template at the beginning was mainly 2 reasons. First of all, we wanted to the concept that we can get efficient light emission from hexagonal silicon germanium based on you still do not hear?
Yeah, well, again, interrupted sometimes. You see the shaking of heads, right? But please continue. I think we can finish this question. Go ahead.
Okay, so, and the second main reason was that gallium arsenide has perfect lattice matching properties, or nearly matching properties, with germanium and the germanium rich alloys. So this was, let's say, start because hexagonal gallium arsenide has been perfectly demonstrated in the field and lots of research about it. So, and for the second choice, I definitely silicon substrates, because this is the next step. And we are already working on it. So there are already, it has been demonstrated in the literature, like the IMEC approach, starting from densified silicon fins, cubic fins that turn due to the stress, like induced phase transformation to hexagonal phase. And also it has been demonstrated in the CNRS group. So this is one of the ways to move towards it. The other way is that we can start from the IBM Zurich approach, that we can try to grow planar hexagonal silicon germanium using these template-assisted epitaxy techniques. So I definitely agree that we should move to silicon-compatible or fully silicon platforms.
Dr. Promovenda, thank you for your answers. In view of time, I need to let this go, although there's plenty of other things to discuss. But thank you so much. And Honorable Chairman, the word back to you. Thank you.
Thank you very much, Professor De Boek. Dr. Vincent, I invite you to continue the opposition.
Okay, thank you, Mr. Chairman. Promovenda, I'm very glad and honored to be with you today, although it is still virtually. You know already, I greatly enjoy reading your manuscript. And of course, among this previous general question, I have many detailed questions to go further in this study and help me to understand what kind of experiments are required to go further. So among this, first, regarding the hypothesis of I3 defects formation during the growth, you hinted evidence that the wet chemical etching of the gallium arsenide core has a great effect on the formation of those defects. You also reported that the concentration of carbon is slightly higher at the interface, but we could also suspect the presence of potassium after the chemical etching. So do you have any idea of the presence of this potassium? And is it possible to try another etching to remove this eventual potassium? And the second idea in the same topic is, does the chemical etching of the gallium arsenide core has an influence on the growth rate of the germanium shell, or maybe on the incubation time?
Zekalair, the opponent, thank you so much for the questions. I'll start with the first question about if I have an idea about the potassium contamination on the surface of the gallium arsenide. So to be honest, we didn't really investigate that into details, but I'm pretty sure that there is a correlation between the chemical etching step that we know it's quite dirty because we know that chemical treatments introduce some impurities or might be roughness in case there is a nanoscale etching or roughening on the gallium arsenide. But knowing for sure if we have potassium or the CN compounds, this is we have no knowledge about it, so we should further investigate it. And for the second question about if we can etch it in a different manner, we actually tried this in the past to etch our gallium arsenide, the gold from the gallium arsenide cores via a potassium iodine solution. But the problem is that potassium iodine heavily attacks the gallium arsenide and it etches gallium arsenide itself. So we have to make sure that we have a selective etchant that only etches gold without heavily affecting our gallium arsenide. So it might be that in the future, if we suspect there is a roughening of the surface of the gallium arsenide due to the potassium cyanide, so maybe we can try to use more diluted solution or more complex etching techniques such that we etch flush, such that we get rid of the impurities. So this is one of them. Or the best case scenario is that we avoid the usage of gold completely from our gallium arsenide nanowires, such that we avoid the chemical treatment. And about the third question, about the effect of the chemical etching on the growth rate of germanium or silicon germanium, let's say germanium, I don't think really that it might affect it, or we know for sure that for germanium, there is an incubation period. So this incubation period, we didn't know specifically what could be the reason. Could it be the termination or the binding of germanium at the very beginning, or the metal organic of germane and its radicals when it binds with the arsenic dimers at the surface of the gallium arsenide, or it could be the residues of the etching. So with that, we do not really know, but I must assure that when we didn't do etching of our gallium arsenide and we just went all the way to grow the germanium shell in the presence of gold, because we know gold does not easily diffuse in germanium, we didn't see a difference in the growth rate. So I suggest that the chemical etching does not affect the growth rate of our germanium shells.
Okay, thank you, Prof. For this question. Again, regarding the incubation time, in your dissertation, you assume that the delay may be due to arsenic desorption, but this is not a polar surface. So I was wondering if arsenide has to desorb and germanium take place instead of arsenide. What is your point of view?
Zechler, the opponent, thank you for the question. So to start with it, yeah, definitely the sidewalls of our nanowires, they are not polar, but we are not sure after the cooling down, for example, if we have more arsenic that somehow deposited on the surface of our nanowires or not. So it might be there are some adsorbed arsenic on the surface that are invisible to us. So this might be one of the reasons. Another reason might be in the incubation time that we also use germane. So it might be that we take time at the very beginning until we crack our molecules, until we get the right radicals to start the growth of germanium. But it has been already identified in the literature that germanium has an incubation time even in the cubic germanium on gallium arsenide thin films. And for that, they try to suggest doing gallium pulsing to speed up the germanium growth or the incubation period at the beginning, which has something to do somehow probably with the arsenic on the surface, because they also investigated that on the different orientations, 111 versus 100, 1110, and etc.
Okay, but did you observe a longer incubation time for arsenic passivated nanowires, for instance?
I don't know, because we don't know really if we have arsenic passivated nanowires or not. This is just a hypothesis because we need to investigate better how to understand this incubation time and, of course, have a control over it.
Okay. Another question regarding the different growing surface. When we expect to make template-assisted growth, I was wondering if the growth is forced to be on the 1,1-2,0 plane, or if there are on both 1-1,0 planes for the growth front.
Zechler, the opponent, thank you so much for the question. So in our case, our shells were somehow forced to grow in the, let's say, following the 1-1,0 facets. So they are really following the same structure of our core, which has the exact same side walls. We didn't observe any rotation of our shell such that it grows in the other crystallographic direction, the 1-1-2,0. So somehow our growth conditions favored the growth in the 1-1,0 side walls direction.
Okay, and do you think the growth is possible on the 1-1-2,0 direction?
Yes.
Maybe it's in the future, but and if it is, could we expect the same I3 defects on such a surface?
Zechler, the opponent, thank you for the question. I expect that shells can, yes, grow in the 1-1-2,0 direction, because we have seen it also in the work of our previous colleagues that if we have extra facets appearing the 1-1-2,0 in our shells, we grow just perfectly hexagonal silicon germanium shells, because it's just another nice direction to grow the hexagonal shells without worrying about switching to the cubic phase. So I expect also the I3 defects to appear in the 1-1-2,0 direction.
Okay, and I have just a small question before finishing. It's a detailed question. Regarding the growth of Verheijen gallium arsenide nanowires, you clearly demonstrate that the deficient gallium content in the draw plate causes staking fault or polytypism. because the effective 5/3 ratio is likely increased. This gallium deficiency is consistent with the tapering of the nanowires that you have observed. But it seems to me it is inconsistent with your mention inflated droplet. As you know, the droplet size scales with the gallium content. So can you explain me this? Or maybe is it an effect during the stopping of the growth?
The opponent, thank you so much for this very interesting question. Indeed, we had the same question when we were trying to analyze our data, and we thought probably that when the contents of the droplet shrinks due to gallium, it has different curvature because it's also gold rich, so it might be having some different interfacial energies that might give us the higher contact angle. So, or not higher contact angle, but this inflated shape that's having the not 90 degrees or this a nice window for the word side contact angle, because word side we expected between something like 90 degrees to 125 degrees. So below it and above it, we expect zinc blende. So it's like going uphill. So you have a nice state for the word side. Below and above, we still have zinc blende.
Yes, but my question is, are you below or above this window?
I think we're above, because we really see at least a higher angle than the 90 degrees that we have observed from the TM images for our nanowires.
I think you are below, but we will discuss about this later.
Thank you. Maybe I should revisit the data again.
Yeah, it's really interesting. Thank you again for your answer, and congratulations for this nice manuscript.
Thank you very much, Dr. Van Stal. I would like to invite the secretary of this committee, Professor Bol, to continue the opposition.
Geachte promovenda. First of all, I would like to congratulate you with this very beautiful thesis. I read it with pleasure as a grower myself, and I have a lot of questions, but I'll try to keep it brief. My first question is about passivation of the hexagonal silicon germanium to increase the photoluminescence, which you briefly touched upon in your last chapter. And you write that you're trying at the moment aluminum oxide as a passivation layer. And of course, you do that with ALD because it nicely coats the full nanowire, and then you ideally, that's the ideal situation in principle. But we also know that aluminum oxide might not be the most efficient passivation layer. So just first a question to start, have you already looked at the luminescence in the meantime after you finish your thesis, or that is still a work in progress?
The opponent, thank you so much for this question. Indeed, we thought about it in the different pool of materials to passivate our nanowires with our colleagues from the plasma deposition for the plasma materials group here in TU Eindhoven. And we thought to start with aluminum oxide because this was the most suitable material for the silicon solar cells, and it got really nice results. So we started with that at the very beginning, and we actually measured luminescence from our nanowires. However, we didn't see a huge improvement. So we do not really know yet, is it the no improvement, is it due to not optimized ALD conditions to coat and passivate our nanowires, or it's really that aluminum oxide is not the suitable material. And we thought also to consider other materials, because this is the negatively charged layer, so we can also look for other materials. So this is another option that we are considering.
Yeah, I'm honestly not so surprised that you didn't see a huge improvement in the luminescence, because if we try the same thing, for example, for the 2D materials, which you also like to have sometimes a high photoluminescence quantum efficiency, we don't see a huge improvement with aluminum oxide either. Another option, especially also for the 2D materials, is the use of polymers or superacids to improve the luminescence. Have you ever came across that for nanowires, and have you ever considered these kind of directions?
No, this is the first time, to be honest, to hear about it. Right. But it's really nice direction to consider.
Well, and then of course you also mentioned episilicon, as a possibility. And of course, then you have the epitaxy layer on top of it. And of course, then ideally you don't create much defects while doing that. But then I was wondering, if I look at the band gap diagram that you have somewhere in the introduction of your thesis, is epi-silicon actually the most wanted kind of epi layer if we look at the band gap alignment of the silicon compared to your silicon germanium?
Kukulad, opponent, thank you so much for the question. The whole idea about epi-silicon, first of all, we have this material source in our reactor, and also that we have full control over its epitaxy because we are experienced with it. So the whole idea was to grow a very thin epi layer such that it fully oxidizes and forms silicon oxide, because also we don't want a big or a thick silicon layer, otherwise it will harm the optical properties of our sample and we will not get the right band alignment. So silicon was just to have a very thin layer to oxidize it later on.
Yeah, but if you then think about, you know, the core shell quantum dots, where they typically take a small bandgap core and a large bandgap shell in order to kind of confine the electron hole pairs within the core. Then you could think also of engineering an epi shell with a certain bandgap that kind of confines the electron hole pairs within the nanowire. Have you ever thought of that? Because now you're thinking epi-silicon and then oxidizing to make a silicon oxide, but maybe you don't even have to do that if you pick the right material.
That's true. So if we are thinking, for example, about a silicon-compatible material, for example, if we have a lower germanium content, maybe we can cap it with a higher germanium content that has more higher band gap. Sorry, it's opposite, higher band gap. So we can do that, and we already thought of these directions to have the heterostructure in our nanowires for that, but we didn't work on it yet.
Right. Okay. Thank you. Then I would like to talk to you about the incubation period that you see when you grow a hexagonal germanium. You see a two regime growth, basically. Yeah? You have the incubation and then it starts growing. And then you found in the literature that this incubation is probably caused by the fact that the arsenium is getting out of the core at the interface, and therefore you can form a gallium germanium interface, which promotes probably the growth. But then I'm thinking, you know, after you have formed the interface, then you start making germanium bonds, obviously. So you're talking, you see a two regime growth, but shouldn't that be a three regime growth then? So the incubation periods where you evaporate a part of the core basically to make the surface ready for your growth. Then the heteroepitaxy basically, yeah, and then the homoepitaxy.
The opponent, thank you so much for the question. To be honest, we didn't observe these two regimes at all. We only saw once we grow a very thin germanium layer, we go directly to the homoepitaxy regime. So it could be maybe that this regime is very small, that I didn't observe it in the sparse data points that I used, because still the data points are not, let's say, representative for the whole range of the growth. So it can be.
Yeah, yeah. Yeah, that's right. That's what I was wondering, whether it's indeed a very short phase so you don't observe it, or you just miss it because you, but yeah, I agree with you. So then related to the, let's see, another growth dynamics kind of question. On page 222, you say in order to have this nice step flow growth, you need a high growth temperature and a low germanium flux. But for some applications, it might actually be beneficial to maybe reduce the growth temperature. And I was wondering if would a pulsed germanium, you know, because if you reduce the temperature, you don't want to increase, you know, or of course you reduce then the atom surface diffusion, and you don't want to over saturate maybe your, or you want to, in some way you want to create super saturation still. But would then a pulsed germanium dose basically help to mitigate that problem?
The opponent, thank you for the question. I didn't think of pulsing before, to be honest, but I thought maybe if we try to balance the different temperature with the right flow. So for example, if we want high temperature, a bit lower flow and the opposite. So if we try to balance both, maybe we can get to the sweet spot regime with the temperature, or try another epitaxial technique with lower temperature. We are using MOVPE. We need higher temperature to crack our metal organic molecules. So if we try to use molecular beam epitaxy, where we have atomic beams already, so we can reduce the temperature because no need to crack the precursors on the substrate. So we can already reduce the temperature a lot.
All right, thank you. I think because of time, I give the word back to the chair.
Thank you very much, Professor Bol. I invite co-promoter Haverkort to continue the opposition.
Dank u, meneer de rector. Geachte promovenda, I first like to compliment you with your very nice booklet. It's very special, how it looks like. But now to the content. As you know, we are working on a hexagonal silicon germanium laser. And for that, we like, say, a nanowire, which is, say, 10 micron high or more. We like a diameter of 1 micron. But also we like an atomically flat surface. And if I look to your pictures in, for instance, supporting figure 5.4, we are quite far from that. So my question to you is, what do you think is most important to reach such an atomically flat side facet, which we know, of course, from gallium arsenide nanowire laser?
Zeker, the co-promoter, thank you so much for the question. This is really an interesting question. So if we start just to look at the image that you mentioned in figure 5.4, looking when we are having high germanium content, we see that our facets are quite atomically flat, and they start to be a bit not atomically flat when we add more silicon. So this suggests that we have, let's say, unoptimized growth dynamics when we start introducing silicon, because this was just the first let's say, optimization experiment for that. So I must say that we didn't spend enough time to optimize the growth dynamics of silicon germanium yet. So I assume these steps might be for a couple of reasons. The first one, if we have already a step flow growth such that we have different steps, so our shells already follow these steps or create these steps due to unoptimized growth conditions of silicon germanium, then we will have steps in our facets. The other reason might be if we have a stacking faults in the core, or let's say the I3 defects in our shell, it might also gives you the illusion of these steps on the shells. So they might not be atomically flat. Of course, I'm not considering the bottom row, because the bottom row here are not really the pure nice hexagonal shells we want, because here strain strikes and takes into effect and then giving us a problematic shell. So because we are using here a thick core. So here we are limited as well with the silicon content that we can introduce with the thick core. So let's not look at the bottom images and focus on the top image. And I believe that we still have room of improvement with the flatness of the silicon germanium shell if we properly control the growth dynamics.
Maybe, well, how important are the defects? Because I understand that if a defect touches the facet, then of course at that point it will not be flat. Do you have any ideas about that? How important that is if the defect touches the outer surface?
Zeker, the opponent, would you clarify the question, or what do you mean by if it touches the surface?
What happens if you have such a flat defect? And what happens with the surface around that? So if there a step at the surface, or if it can just be flat, what do you expect to happen there?
The opponent, thank you for the question. It depends on the type of the defect. For example, looking at the zinc blended defect, we have an ABC that looks like a tilted line. So you might have the step looks like a tilt here, for example, or the other side going with this angle, right? So this is, for example, an I1 or I2 defect, which is just a normal cubic stacking fault in our nanowires. If you look to the I3, it looks like how do I call it? Like a side V that has the as if it's a twin. So it has first a tilted line up and a tilted line down. So depends on the type of the defect that you will have a different type of a step.
Maybe a final short question. Do you think it helps to try to enhance the surface diffusion across the facet? Because that's what you do in 2D growth. Is that possible here to further enhance the diffusion of atoms?
The opponent, yes, this is one of the mechanisms that we already are trying to work on it and to combat, which is one of the formation mechanisms of these I3. If we have limited diffusion or slow diffusion of atoms, then we enhance the density of the defects. So if we try to control the mobility of atoms, we can get rid of it. And of course, if we try also to even lower the number of defects by controlling impurities and interface, we can also reduce the number of the steps at the shell surface.
Maybe the last question is: do you think it's possible to? Do you think you need a very thin core because then the strain is less? Is that an important thing, or can you also do it with a thick core with much more strain?
The opponent, thank you for the question. I believe that the thinner the core, the better that we can have for our structures, because we have seen already from the results that I presented in chapter 5 that the thinner the core, the more silicon I can add to my shell, such that I can extend the whole range of compositions. However, here, for example, beyond 88% of germanium, I started already to get completely faulty or different faceted regimes, or a completely not a hexagonal structure or a defected structure, which means a strain can induce a huge amount of defect, destroying the beautiful structural quality that we have already claimed for hexagonal structure. So I assume a thin template to start with is very important, especially if we are lattice mismatched, like a 2%, for example, between 50% silicon germanium and gallium arsenide.
Okay, thank you. In view of time, I leave it.
Thank you very much. Co-promoter Verheijen, please continue the opposition.
Geachte promovenda, once again, congratulations with this beautiful piece of work. I have a few questions on topics that we did not discuss, and I think we have many discussions. My first question concerns the precursors that you used. J.E.M., a fellow PhD student who worked on silicon germanium growth earlier, used tetrasilane instead of disilane for the growth. My question is whether you see options of improving the silicon germanium shell quality by using other precursors than the germane and disilane you used, for instance, monosilane, tetrasilane, digermane. Can you explain the possible differences and maybe the merits or disadvantages?
The co-promoter, thank you so much for the question. So indeed, our fellow PhD showed that tetrasilane is advantageous in terms of cracking at lower temperatures than disilane. So if we take it by comparison or analogy, then yes, having a longer chain of germanium like digermane, for example, will be better than germane, because germane has a stronger bonds between germanium and hydrogen more than the germanium bonds in the longer molecules. But also be careful that in my case here, I used only disilane. However, my colleague used tetrasilane. So I have a room of improvement in both precursors, in the silicon precursor and the germanium precursor. So let's say if we use quite comparable precursors, we can reduce the temperature of the cracking. But I'm afraid, to be honest, from the complicated cracking dynamics of these different molecules, because I have germane and a disilane, and imagine now I have tetrasilane and germane. So it might be that tetrasilane cracks at very low temperatures and germanium at much higher temperatures. So one of them might be easily incorporated than the other one, and giving me a problematic growth dynamics. And so for that, we have to be careful with the selection of the precursors to be able to crack nearly comparable, or best case scenario, again, as I'm saying, molecular P.E.M epitaxy when we're having pure atomic or molecular beams without the need of cracking our precursors.
Okay. Another question, if you look at on page 137, you show the growth rate of germanium, and it's about 20 nanometers per hour. Can you think of ways to increase the growth rates while maintaining a good crystalline quality of your wires?
The co-promoter. So thinking about increasing the growth rate, so it might be if we increase the temperature more, still within the limit below the desorption of germanium or the re-evaporation of germanium. So we might crack more germanium and we get higher growth rates. We can also use higher flows, which is actually the simpler trick. Use higher flows than what I used, but with that I have to balance again the temperature. Otherwise, I might end up with unbalanced growth dynamics that introduce more I3 defects.
So is there room for improvement still in growth rate, do you think?
I believe yes, because we were working with very slow growth rates and very low flows with 70 cc.
Dank u wel, meneer de Pedal. I request the candidate and the two assistants to take your seat in the hall again. In a few moments, I will adjourn the session. The committee will then retreat for deliberations, and I would like to invite the committee members who are online to leave this meeting and to go to the closed meeting. The session is adjourned.